Let's go ahead and continue with an example problem here. So let's take a look at this. It says a piston cylinder device contains steam initially at 1 megapascal, 450 C, and 2.5 cubic meters. Steam is allowed to cool at constant pressure until it first starts condensing. Show the process on a TV diagram with respect to saturation lines and determine the mass of steam, the final temperature, and the heat loss. So let's start with a schematic. I'll draw my schematic, my piston cylinder device. I have water inside my system. This is a cooling process, so I have heat leaving the system, resulting in my piston moving down. I'm going to go ahead and draw some assumptions. Number one, I'm going to assume that this system is stationary. Two, I'm going to assume that my water is not an ideal gas. Why do I say that? Because one of the biggest assumptions you need to remember is stating what is inside the system, right? That helps you to be able to determine how you're going to evaluate your properties. If it's an ideal gas, well, you'll be able to go to use the ideal gas law, right? If it's a phase change substance, you're going to have to go to the tables in order to quantify the properties. Now, there's some ideal gas tables too that we'll eventually cover. But you have to remember that what we're going to do in this class is no matter what state that water or refrigerant is, we're not going to assume them to be an ideal gas. So since we have water, we're going to rely on the tables to define the properties and not assume it to be an ideal gas, even if it's a superheated vapor. Number three, I'm going to assume it to be a constant pressure process. And this is a closed system. Okay. So let's go ahead and let's go do this step by step. We're going to do a first law analysis. Step one. We write out a first law. E in minus E out equals delta E system. Step two, we quantify our energy terms. Now I have E in, which is boundary work coming into the system. We're going to quantify that as negative because energy work to the system, which we quantify as negative. I have heat leaving the system, so Q out equals change in energy of the system for a stationary system, which is only delta U because delta KE and delta PE is 0. So I'm going to go ahead and put Q out on one side of the equation, and I'm going to put delta U and boundary work on the other. There's my first law. Now I'm going to go ahead and I'm going to call this step 3. I'm going to define my boundary work. In this case, I have a constant pressure system, right? So if that means my boundary work is going to be pressure times change in volume, or more specifically, mass times pressure times change in specific volume. So then my first law simplifies, or actually I guess you could say expands, to become, if I want to quantify my change in internal energy, it's going to be mass times the change in specific internal energy because it's a closed system, therefore the mass is constant, therefore I can factor out the mass, plus mass times pressure times change in specific volume. Now I can also go ahead at this point and simplify this even more, because we looked at earlier, right, that enthalpy is equal to, specific enthalpy is equal to specific internal energy plus pressure times specific volume. So this whole equation can simplify down to Q out is equal to mass times the change in specific enthalpy. Now what's next? Now let's go ahead and evaluate our properties. I need H1 and H2. I need two properties of state 1 to get H1, and the same thing for state 2. So next we'll do that. According to the problem statement, it tells us that an initial pressure is 1 megapascal, and the initial temperature is 450 degrees Celsius. At this point, I can go ahead and go to my tables or use engineering equation solver, right? The program that we have now introduced to you, that I have introduced to you guys, the computer program that you can use to evaluate your properties. Go ahead and I can find my specific volume at state 1. And I can use that specific volume to find my mass, since my mass is not directly given to me, right? Mass would equal the initial volume divided by the initial specific volume. That gives me a mass of 7.6 kilograms. State 2, I know the pressure is the same as state 1. And the problem statement tells me, if I go back and reread it, it tells me that the steam is allowed to cool at constant pressure until it first starts condensing. That means it's a saturated vapor. Saturated vapor means, it basically means that it's just starting to condense. So I know that this is a saturated vapor. So I can go to my saturated tables or use ease and plug in a value of 1 for the quality, and the pressure would be 1 megapascal. And I can find H2, right? Again, which would be the enthalpy of saturated gas at a pressure of 1 megapascal. That would be equal to 2,777.1 kilojoules per kilogram. And I can get the temperature too, which happens just to be the saturation temperature. So it's Tsat at a pressure of 1 megapascal, which ends up being 180 degrees, which happens to be part of what the problem is asking for. Also, the problem asks for the mass. And for state 1, I forgot to mention, I apologize for that. You pulled out the specific volume. You can also get the enthalpy pretty directly as well, which is 3,371.3 kilojoules per kilogram. We have everything we need to finish off the problem, so we get that Q out. From the last slide, we figured out that Q out is going to equal mass times our change in enthalpy. So at this point, we have all our unknowns, and we can figure out that the amount of heat that was removed from this system was 4,495 kilojoules.